Well, first of all, I would ask you if you could just write your names and which grade are you, which year of which program from Caltech or from here, just for me to understand well, for whom I should read this course. Just I would like to ask this. Well, in English or in Russian, it doesn't matter. The course will be in English. Well, I see that there are participants who speak Russian, and at least there are also some such participants online. And okay, what will this course be about? It's a kind of some rather introductory maybe course in differential topology. It's the same as topology of smooth manifolds. Generally, I would like to cover two main topics. The first is the rank homology theory, and also this leads to characteristic classes. From that viewpoint, there are a lot of possible points of view on characteristic classes. I'm going to discuss this one. And the second part will be Morse theory. And I hope that I will be able to speak about Smale's Ash composite theory. So I would like to have in this course not only some introductory notions, introductory theorems, but to have at least one actually important and hard theorem, and so I hope that we could go through it, and possibly the order will be another. Possibly I will speak some words about the rank homology theory, and then we come to Morse theory, and characteristic classes will be the end. And in fact, characteristic classes is the part which, if we have small amount of time, then it will be without this part. The matter is that there are a lot of other courses where this point of view. This is also called shared wave theory, and there are a lot of courses where this is discussed. So I hope we have time for this, but there is some probability that not. Okay, so maybe before we start more or less consecutive course, I will say some words on the subject in general. The matter is that when we have a smooth manifold, we have more information than only homotopy information. This subject is the idea is that we can okay, we have homotopy topology. We can consider homotopy groups, homology groups, build all this technique just of homotopy theory. And the main goal of homotopy theory is to translate homotopy problems of say homotopy groups of spheres, to some algebraic problems. The second question is whether we can solve this algebraic problems or not. Usually not, but still it is a success if we can translate some topological homotopy problems to algebraic ones. For when we have smooth manifolds, first of all we have more than just a homotopy type of this, and even more than just topological type. It is very important that we have as any smooth manifold is automatically endowed with vector bundle over it, and then we can use all the technique of vector bundles. We can, starting from just one vector bundle, we can use some constructions from linear algebra to produce other vector bundles. So, say we have this tangent vector bundle, we automatically obtain cotangent vector bundle, which is dual to that, and we automatically obtain, say, exterior powers of this bundle, and so on. All the technique from linear algebra. And so we have some machinery which we do not have for usual for arbitrary topological space. On the other hand, the problems are also harder. For arbitrary topological space, the usual problem is whether two spaces are homotopy equivalent, or whether or how to compute, say, the set of homotopy classes of maps from X to Y. When we say about smooth manifolds, we are more interested rather in questions whether two manifolds are diffeomorphic. So there are smooth mutually inverse maps, or whether what is, say, the set of embeddings of M1 to M2 or so on. These questions are much harder than homotopy questions, and actually in differential topology our usual goal is to translate if in homotopy theory we would like to reduce topological problems to algebraic ones, here we usually want to reduce this topological problem, smooth topological problem, to homotopy problem. Again, after that, we understand that this homotopy problem, sometimes we can solve it, or usually we cannot solve it, but still homotopy problems are easier, and this is what we usually want. For instance, just this is a part which maybe I hope I will be able to say some words here about smooth structure on spheres. These are famous results first by Miller and then by Milner-Kervier. And this is just the kind of such question that, okay, what is smooth structure of spheres? We would like to answer a question. We have got a usual n-dimensional sphere. It is a smooth manifold. But we can ask about smooth manifolds M such that they are homeomorphic, but not diffeomorphic. So they are identical in topological category, but not in smooth. And we may ask how many such different smooth charges, how many different manifolds of such kind up to diffeomorphism exist. And here, this is the topic, well, when all these things are joined together. But I would like to say that, okay, there is answer, which was obtained by Mill and Carrier mostly. Answer is through homotopy groups of spheres. They just enter here as a part of this answer. So we can write answer, but and nobody knows how to compute homotopy groups of spheres except for several first. And but still, this is a good answer in the sense that we reduce topological problems to homotopy one. Okay, well, and just maybe I would like to say some general words about this Smale Ashkenazi theory, which will be the main goal of our course. The main idea, I would just like to formulate it so that we know where we are going to. So, what is cobordism? Cobordism is just a manifold with two given boundaries. So, if we have two smooth manifolds, M1 and M2 of some dimension n, they are said to be cobordant if there exists here a manifold with boundary of dimension n plus 1. All manifolds are smooth and with the boundary consisting of those two manifolds. Usually, well, I'm not going. I don't want to go into details now. Usually, when one speaks about, say, oriented manifolds, you need only also care about orientation. But at the moment, I don't want to say about it. Okay, and this is just cobordism, and it is called Ashkenazi if both inclusions of bases are homotopy equivalents. Well, and wonderful theorem by Smale is that if our manifolds are simply connected, okay, if we have an Ashkenazi, then M1 and M2 are homotopy equivalent, so it's enough to say that one of them is simply connected. Then M1 Ashkenazi and n is greater than or equal to 5, then if two manifolds are Ashkenazi, we can say that they are diffeomorphic. They are just the same manifold. And also this Ashkenazi is just a cylinder up to diffeomorphism. So this is a very hard and strong theorem, and the most important in this theorem is that okay, we have some conditions like that, but an important thing is that all these conditions are just homotopy conditions. We require something, but we require only homotopy things. Homotopy is much easier to check usually, and actually why this theory is important. It's the main, and I would say the only. This theorem is, I don't remember exactly, but something about 58. Since then, we still do not have any other tool to prove that two manifolds are different. This is more or less the only tool in topology which allows to prove that two manifolds are diffeomorphic. Of course, except for in some very easy cases we can just construct the diffeomorphism by hands, but if we are in more complicated situation when we cannot construct it explicitly, then this is more or less the only thing which we can. Of course, this theorem, we have some generalizations of them since then for non-semi-connected manifolds and so on. So there is this theorem and its generalizations, but this is the only approach. Almost nothing else exists. Okay, so this is what we are going to, and in particular, if I hope, if we have time, this will imply multidimensional concurrent conjecture. What says the concurrent conjecture? The concurrent conjecture says that if a manifold is a homotopy sphere, if it is homotopy equivalent to a sphere, then it is homeomorphic to a sphere. This is not directly implies, but this is a result of. This is not a question mark. Okay, this is not so direct. It is not a direct corollary, but using the same technique and using this result, the multidimensional concurrent conjecture was proved by Smale also, and in topology usually we have like an old joke that we can count 1, 2, and many. In topology is something like that. That we have dimensions 3, 4, and 5 dimensions. And all the topology splits into 3 parts, more or less. Well, dimensions 1 and 2 are usually easier, so it is not so important. But then we have this trichotomy, and all this story is only about this part. 3 and 4 are harder, and we will not speak about it. We will only see why it doesn't work. The same proof in dimensions 3 and 4. Okay, so that's some general words, and now let's some words about several first lectures. Well, and is there this list which I...
Yes.
Okay, it's here. Okay. Well, maybe I should skip some obvious things because several previous time when I read a similar course, there were mostly students of 2nd and 3rd year, and so okay, if everything will be too easy and not interesting, just say me and I will try to become faster. we need some things about from differential geometry. This is the base for all our considerations. And from time to time, I will try to remind some, or to recall some things. And if it is too obvious, then just we will try to skip it. But if it not, then just... Well, so let us start from first. What I would like to say about is the definitions of Differential homology. And to define Differential homology, we will need to speak about differential forms. First of all, my object will be usually, my object is always a smooth manifold. At least today, I always assume that it is without a boundary, but maybe non-compact. It's okay if it is not compact, but without boundary for today. Okay, if we have such an object, then we have a tangent bundle. This is vector bundle with. It's okay. Vector bundles are okay. Yes. Just also say me if I need to explain something. Okay, we have a vector bundle, tangent vector bundle, cotangent vector bundle. It's just dual vector bundle, and yes, almost all the story which I speak about will be real. We very few times in this course we will consider something complex. So mostly real situation, and we have exterior powers of cotangent bundle, and actually K-form, differential K-form, is just a C infinity section of this vector bundle. C infinity smooth section of this vector bundle. This is invariant point of view. If we would like not only to speak about K-forms but also to work with them by hands, then sometimes we need to write them down in coordinates. Well, and then I just recall some basic things that okay, if we have local coordinates, well, then we have the corresponding tangent basic coordinate vectors. This is basis in tangent space. Yes. And we have dual basis of cotangent space. Okay. Which of these guys depends on x1?
Point.
Well?
Point.
Oh, okay, yeah, at some point. Which of these two guys depends on x1? Just and
It's differential dx1.
well,
It's differential dx1.
the differential, yes. This one depends on the x1. This one doesn't depend on the x1. This is just a good point to think through. If you are interested in these basis vectors, then this guy depends on all coordinates, not on the x1. This is differentiation of function. If you would like to differentiate the function of x over x1, you need to say which coordinates are constant. If we differentiate with constant x2, this is not the same as we differentiate with constant x1 plus x2. So these guys are not defined only by one column, but these are, and actually the differential of any function can be written just in, okay, this is as an element of cotangent space. Yes, I just recall one important. As an element of cotangent space, it has value on a vector, and this is just the result of differentiation of function f along vector. We go along vector and differentiate along in this direction. So this is an important formula, and it is completely invariant formula, and it is very useful to us. Sometimes notation here is big C of f, but it is just the same. We just identify vector fields with differentiation, and well, there's no difference here. Okay, of course, this is again, this is just equality of smooth functions on M, and of course we can restrict it to any point, and it is equality in any point. Okay, I hope that, well, and the next one is that, of course, a basis of the exterior power. Okay, it's better to restrict to a point of exterior power of the space. Of course, the basis is formed by some such monomials, and so any differential form it can be written as such some coefficient, which is smooth function on M. And these monomials. Okay, this is just some reminder that sometimes we will need to write it explicitly, more or less. Well, what do we need about differential forms? We have got several operations on them. First of all, as we have just again from linear algebra for each vector space, we have exterior power. We can take exterior power of two exterior forms. So if there is such man, of course. And certainly this immediately, yes, I would like to introduce notation that this is notation. Omega k of M is just the space of all differential k forms on M. And so we immediately obtain this exterior power of forms, and what we immediately have? We immediately have, of course, it is associative, and it is commutative up to a sign. And the sign is that when we swap two differential forms, we get a sign which is equal to the product of their degrees. So these are basic properties, and they immediately follow just from linear algebraic properties of this usual map. And what? Well, and another important thing which we have is exterior differential. This is a natural map from K form to K plus 1 forms. Well, and okay, if you would like to use invariant approach, then what do we need? We can write down some properties which immediately, which uniquely characterize this differential. Namely, I'm sorry, I just, only now I erased the first important property. That when we take the differential of zero form, then it is just like that. Okay? If zero forms are just, of course, this is the same as just smooth functions on M. Or smooth everything always means C infinity. All things can, many things can be said for also for some finite smoothness, but for simplicity I always consider C infinity. Well, second is that says how it looks on one forms, at least on differentials of it is zero. If f again is a smooth function. And third is that we have Leibniz rule that we always have this one. Okay, a good exercise that these three properties characterize exterior differential uniquely. So there is exactly one map that satisfies. Oh, of course, it is also linear in sense that not linear with respect to multiplication by functions, but linear with respect to multiplication by number. So it's linear and satisfies these conditions. Then the exercise is that these properties characterize D uniquely. And in coordinates, we can write it down as the sum of J and the sum of these guys. Partial derivative over xj. In fact, here it is almost impossible to avoid this coordinate approach. The matter is that it is rather easy to show that that these three properties characterize D uniquely if it exists. But if we would like to prove the existence, at least an easier way is definitely an easier way is to write down it like that and to check that it is independent on coordinates. All other possibilities are more or less tricks that say the same but avoid worse coordinates. But still more or less it's the same. Okay, what do we need about exterior differentials? Again, we will need some basic properties. First of all, that d squared is 0. we require it for functions, but actually it follows for all forms. And also, the Leibniz rule is already there. More or less, that's all what we need. Okay, so external differential plays the key role in this situation, and actually this property plays the key role. Again, we can deduce this from these properties, but from coordinate expression, it is just straightforward. The matter is that when we take the second derivative, we obtain second derivatives of these coordinates, and they are equal to each other, and they just cancel. Okay. So once we have this, we can consider this Dirac complex. We can consider the Dirac complex just 0 to 0 forms of M to 1 forms of M and so on. We have n form of M, and certainly we have no forms beyond this dimension, since just this becomes trivial. Exterior powers, and once we have differentials of which squared is 0, we can define homology. As usual, once we have chain complex, we can define homology by taking kernel of this map. By the image of this map. Okay, and well, and maybe before. So this is definition, this is main object which we are going to discuss, and maybe before going to a general situation, let us consider in more details one forms. The matter is that, yes, terminology, these are exact forms which are, these are closed. I'm sorry, I forget English word for them. Closed and exact forms. Okay. Before speaking of general situation, let us let us consider in more details the case of one forms. This is the most important case, actually. One forms. So an important thing about one forms is that if phi is a one form, and if it is closed, if we have the phi equals 0, then locally we have that phi is a differential of the function. This is only locally, so in a neighborhood of every point, there is a smooth function such that phi is the differential of this function. And just maybe you know it very well, but still I would like to say some words about how to prove it, because we would have a similar situation in higher dimensions also. Okay, how one can find this function?
It means it is a long-term theorem.
Yes. Well, I would like just to say, okay, if we start from some point p, like this, we can start integrating one form and over some paths starting from p. And an important property of closed forms is that if two paths are homotopic, then integrals are equal. Sorry. Well, and and why? Just because if they are homotopic, then we can consider a map from a disk to here, such that on this side we see gamma 1, on this side we see gamma 2, and here we have some map. And important things that when we work with smooth manifolds, it is usually hard and to approximate some map by an embedding, by something, but it is completely no problem to approximate a continuous map by a smooth map. This is just a general thing that we can always approximate continuous maps by smooth maps. It is almost obvious, but it is important that we can do it. Okay, and then we can just write down, yes, recall that for cotangent bundle we have pullback along smooth maps, and so and this pullback computes with all our operations, let's say with differential, and so we can just write down that this difference, is just, okay, let these lines be L1 and L2, it is just, we can take pullbacks, and this is the integral of pullback along this boundary, and here we have the most important things here is that we have Stokes' theorem that it is the integral over disk of d phi. So and now it is 0. Well, so this integral is independent, and so we can locally define the function f of q as integral from p to q of our one form phi. And locally, if we are in a neighborhood of p, then this integral is independent on the path, and this is a good definition. And then we have df equals phi. Okay, so locally it is an exact form, but so the only thing is that closed form can have non-trivial integrals over loops which are not null homotopic, and integrating this along these one loops just detects our zero homology classes, and this is this picture for one forms is typical in higher dimensions as well. Again, from Stokes' theorem, we will obtain that so we will come to the fact that we can integrate closed key forms about integrate closed key forms along singular cycles. And finally we arrive to a pairing between these de Rham homology groups and singular homology of M. Well, and we need to go through some technical problems, but we will be able to do this. Okay, what still? Could you tell me who? Well, Poincaré lemma in general situation is this known to everybody who do not know what is this?
You mean that one?
That one, but not for one forms, but for k forms.
Yeah, I think it's clear.
It's okay. Then I just skip it because okay. I was going to say about it, but I just formulate it in. I just formulate, and of course I skip the proof. So. Poincaré lemma is that okay? If we have more or less, it says that the de Rham homology of Rn is R in dimension 0 and is 0 in positive dimension. So in positive dimension, any closed form is exact. Okay, and actually we will need maybe a more important formulation. So if you do not know this formulation, this is a good exercise. That actually we can speak not only on how to prove this lemma. I don't want to go to say a proof, but one of possible proofs proves it by induction on n. We go from Rn to Rn plus 1, and actually the step of this induction is as follows. For any manifold M, we can consider M times R. And we can compare it with M. And we have two maps. We have projection here, and we have inclusion just as zero section. And well, each smooth map gives us pushback, pullback in differential forms, and hence gives us pullback in de Rham homology. So we have in de Rham homology we have I star in this direction and I star in that direction. And claim exercise is that they are mutually inverse isomorphisms. And of course, Poincaré lemma immediately follows from that. For point, it is hopeless, and then we proceed by induction. Well, as far as I understand, I'm sorry, it's time to finish. Yes. Now, I always forget what's the length of.
1250.
1450. Мы в 11:30 начали и
We suddenly, yes. Oh, that's wonderful. Sorry. It's okay. Then we proceed.
It can be proved independently on Poincare lemma.
Yes, it can be proved. Actually, it can be proved just in the same way as Poincare lemma. Just usual proof of Poincare lemma literally transmits to this case. What's the main idea behind Poincare lemma? At least we have one. Just few words. I don't want to go in details. This is a good exercise to do this. Of course, it also can be deduced from here, but actually we just do not. It is easier to prove this and then deduce Poincare lemma. If we have this direction R and we have M here, then any one. How does it look any form on the product? Actually, we have forms of two types. The first type is let x be a point in M and t be a number in R. First, what is possible? We can take any smooth function here, multiply it by a form. Omega is a form of M. But it's better to say, but multiply it by a pullback of this form. And okay, that's nice forms on the total space. Well, but also we have forms like that. So in coordinates, if we consider coordinates in the base, then there are summands where dt enters this form, and there are summands where it doesn't enter. And we can split them in such and such summands. And using this splitting, it is rather easy to write down a chain homotopy from well, how we usually prove that two maps are mutually inverse in cohomology. We consider those maps not in cohomology, but in forms. We can consider the same maps in forms. Well, then look, in one direction, if we consider I and then pi, then it is identity map. So if we consider pi star and then I star, then it is identity. But in the opposite order, it is not identity. So we need to introduce a chain homotopy between. We would like to have a chain homotopy between this one and identity. And to have such chain homotopy, we need a map from here to omega star plus 1 M. And it can be more or less explicitly written forms of these types. And actually, Poincare lemma is also usually proved in such a way. It is more just if you go through usual proof, then if you see that in fact you can prove this. Okay, I think that we can skip it as an exercise. Okay, and the next important, well, what is the most important property of homology, of any kind of homology? The most important property is that of usual, say if you construct usual singular homology or simplicial homology or any kind of homology theory, then what is important? An important thing is that you have a long exact sequence of a pair. And for homology or cohomology. And for the round homology, we would also like to have something like that, but we cannot hope to have it exactly. The matter is that, a long-exact sequence of a pair is useful only together with understanding that for good pairs, this is the same as the quotient. For good enough pairs, I don't want to go in details now, say for CW pairs. Without this, it is rather hard to work with. And this is a bad object for us. Of course, the quotient of two manifolds is by no means a manifold, and we cannot define the RAM homology here. Hence, instead of long-exact sequence of a pair, the same role is in fact played with another long-exact sequence, namely with Meyer-Vittorius long-exact sequence. I'm sorry, I forget to look on how they are spelled. Maybe it is not directly this way. For usual homology, it is more or less equivalent to long-exact sequence of a pair, and it is much more convenient for us in once we would like to work with manifolds. And so the situation is as follows: that suppose that our manifold is the union of two open subsets. Then we have, then actually we can consider, well, then we have such maps. We have the intersection. It can be embedded to U, it can be embedded to V, and then it can be both of them are embedded in M. Okay, here let these inclusions be I1 and I2 and these J1 and J2. Then we have such situation that we can consider the forms, K forms on M. Then we can restrict them to U, and we can restrict them to V. And then we can restrict both of them to the intersection. But the only thing is that here we need to take the sum of pullbacks, and here we need to take the difference of pullbacks. Or vice versa, it doesn't matter. Sum and one. And well, okay, my claim is that this sequence is exact. Well, why? Let us understand what is not obvious here. Exactness here is of course obvious if we have a non-trivial K form, then it is non-trivial in at least one point. This point is either in V or in U, then it is non-trivial in at least one. So this is inclusion, this is obvious. Here, exactness in this. Okay, first of all, if we restrict a form from M to U and V, and then restrict to the intersection and subtract one from another, of course we get zero. vice versa, if we have a form on U and a form on V, and they coincide on the intersection, then of course we have a well-defined form on M. So again, exactness here is also obvious. The only non-obvious thing, slightly non-obvious, it is still very easy, is exactness in this term. Namely, y is a surjective. So assume that we have a form here. How to construct a form here and a form there, which such that the difference is this phi. What is non-trivial here? The matter is that, okay, let this be U, let this be V, just like picture. Then the form on the intersection can behave badly near those points where our manifold ends. So it may go to infinity. It is just so we cannot just lift this phi to one of those forms. The idea here is to use partition of unity. I would like to formulate the theorem, of course I will not prove it, that we have C infinity partition of unity. Partition of unity. What is this? If we have an open cover of a smooth manifold, then there exist smooth functions, again C infinity smooth as usual, and with support of each rho alpha contained in U alpha. What is support? Support is the closure of those points where the function is non-zero. It is important that the closure of them. So the function is not only the function is zero outside U alpha, but actually the closure of those points where the function is non-zero is contained in U alpha. And then this is the first, and the second, it doesn't depend on what is the cardinality of this cover. In a neighborhood of every point, the second restriction, in a neighborhood of every point, only finitely many of these functions are non-zero. And we have, yes, they are non-negative, and we have, this is identically one. Well, this is standard theorem on partition of unity, and we will use it often throughout this course. And how it helps here. Here we can consider partition of unity subject to this cover by just two sets U and V. So we can find a function rho u will be like that. It is non-zero only the closure of those points where it is non-zero is contained in U. The function rho v will be like that. Well, and then even if phi behaves badly here, we can consider if we take rho u times phi, then it is a well-defined function, one form where a well-defined one form on V. So rho u times phi is well-defined form on V. To be more precise, we continue it by 0. The matter is that the initial form can be continued to V by 0. The matter is it can go to infinity. Here it can behave badly. But rho u times phi is 0 in all these points, so it is a well-defined form which is more precise. There is a form, let it be phi v, such that it is equal to rho u phi times phi on the intersection, and it is equal to 0 on the outside u. And similarly, we have u, which is rho v of phi on the intersection, and it is 0 on the component u without v. And then once we have these two forms, then of course, if we consider here what we should consider, we should take phi u, well, and minus phi v. Then this pair goes to phi. Just in obvious way. So this is easy, but we need this trick, otherwise we cannot do anything. And well, and next. Of course, now we have just a purely algebraic fact that once we have chain complexes, and we have, of course, these maps are chain maps, they commute with the differential. So once we have exact sequence of 3 chain complexes, we immediately obtain a non-exact sequence. This is pure algebraic thing. And how does this sequence looks? Okay, we start with kth homology of M. We go to kth homology of U plus kth homology of V, and again this map is just the sum of pullbacks. Here we go to kth homology of the intersection. Here we take the difference of pullbacks, and here we go to k plus first homology of M, and so on. So, as usual, we have this non-exact sequence. Well, and a good, this one is connected homomorphism, which is usually denoted by T star. And well, and the good question is, in fact, it is a powerful tool for study, for computing homology, first of all. But it becomes even more useful if we are able to write down this term explicitly. It is useful to know that there is such a map, but it is even more useful to know that we can write it down explicitly. And the question is, well, how to write it down? Generally, how to just let us study the algebraic part. Okay, if we have just 3 chain complexes, just 3 chain complexes, well, chain complex R, N. Oh, okay, I will prefer co-chain notation. We have this complex, we have complex E, and we have complex C. And we have chain maps which makes it an exact sequence in each dimension. Okay, how to then in this situation we have a non-exact sequence, yes, from cohomology of this complex, and we have a connecting homomorphism from cohomology of this complex, from nth cohomology of this complex, to the n plus first cohomology of this complex. How to proceed in algebraic situation?
No, we need to look how cycles transfer from
Yeah.
diagram.
We need to consider here a preimage, yes? So we need to find here a form, an element which goes here. Then we need to go downstairs, yes? And here we know that we are going.
It is in the kernel.
Yes,
hence
in the
it
kernel,
comes
and
from-
hence it's. Let us do it in our situation. In our situation, we start with the form, and we would like to go here, but we have done it just now. We come to this pair of forms. Then we need to go downstairs. What does it mean to go downstairs? To take the differential. Yes? So, I'm sorry, going downstairs, we arrive to differentials of these forms. Yes? And then we need to go to the left. And look, these differentials coincide on the intersection. Because the initial form, they do not coincide for an arbitrary initial form, but we start with the closed form. Once we have an element an element of their homology, we start with a closed form. And once we start with a closed form, then these two differentials coincide on the intersection because their difference is defined, that is 0. So we have a preimage here, and it doesn't matter which of them we take, yes, because they coincide on the intersection. We take the I'm sorry. One more picture. Here we have U, and here we have V. Yes? This is V, and this is U. What can we say about these forms, d phi U and minus d phi V? First of all, they coincide on the intersection. But second, look, the support of this one is contained in V, but the support of that one is contained in U. So the support, but they coincide on the intersection, they coincide to each other. Hence, in fact, their support is contained in the intersection. And this is why we can continue the but 0 to the whole m. And this is exactly what we need. What is the result? The result, and this is claim which will be often used, that we can write down this star explicitly. If we would like to apply this star to the cohomology class of a closed K-form phi, then we need to proceed as follows. We need to consider the partition of unity and we need to take the differential of, say, rho v of phi. And this is a well-defined form on the whole manifold. Phi was on the intersection, but this one we can continue it by 0 to the whole manifold M and take the cohomology class. Well, but and the same, this is the same as to take minus d of rho u of phi. So phi was closed, hence the sum of rho v of phi and rho u of phi is just phi. So its differential is 0, and hence we have these two possibilities. It is not important which sign to choose, but it is convenient to understand that we have this particular expression for this star. Well, and now it's time to finish. We have just few words that we will have this part of lecture, and the second part of the break will be more about some problems. Sometimes there will be some list of problems. Today it will not be like that. We just discuss several problems in general, which seems to be important for me. So the second part will be not a lecture, but I hope it will be more interactive with you. And okay, so now let's have this break.
Я не очень знаю, стоит ли вторую часть писать, потому что...
Что писать стоит?
Что? Я очень надеюсь, что говорить буду не только я.
Нет, это
И тогда это просто не мое кино будет.
в этом смысле.
Да.
Не передавать же совет микрофон. Ну, сейчас посмотрим, ладно.
Нет, наверное, писать стоит, а там решат.
Да, там нет, не сложно эту штуку надеть. Ну, смотрите, сегодня нет, а дальше будут листочки, которые можно рассматривать, потому что да.
потом я как бы без него еще выходит. Поэтому это надо обратиться, если вам было бы интересно. Может, мне было бы интересно с вами заниматься. Я знаю, что я его сын не беру.
Смотрите, ну, просто который вопрос, два разных вопроса. Один, что есть возможность, что продолжить с работать, что сегодня не понятно, что кто-то говорит.
Ну, я рассматриваю тоже поработать уже. Было бы интересно.
Давайте тогда немножко судьбу. Да, да, то есть теоретически можно говорить, понять, что вам интересно.
Я могу вам показать самый результат работы, например, чтобы они будут лучше понятны.
Ну да, давайте немножко поговорим. Значит, сейчас я... В принципе, можно... Давайте вам телефон, да? Ну, как-нибудь договоримся. Ну, или вот сегодня в конце договориться. Давайте я напишу. Договоримся, когда удобно.
Я еще тоже хотел вопрос. Интересно, вот хочется узнать, насколько я знаю, раньше не было разделения единиц. Ну, то есть, когда была дифференциальная топология, не было этой технологии.
Разделение единицы, да. Нет, во-первых, в топологическом контексте, значит, тут бесконечные да? В топологическом контексте уже точно в 20-е годы.
Но в Панкаре не было.
А в Панкаре ничего этого не было.
А как он тогда? Что было в Панкаре?
Ой, у Панкаре, если взять работу по гномологии, там ни одного утверждения, которое с современной точки зрения выдерживает строгость. То есть это вот такая, она очень, с одной стороны, очень глубокая работа, потому что там сразу очень много всего понял. С другой стороны,
Там не было заканчиваться точной последовательности.
не было ничего. Потом потихоньку все алгебраизовывали, разбирались, как это аккуратно формулировать. Ну, тем более, для рамок это вообще, конечно, не совсем плохо. Там скорее что-то похожее. Тоже, если бы раньше не было, у него было понимание, что циклы как геометрически строятся, а вот в каком смысле, то есть иногда цикл называл многообразие, иногда я так это пытался.
Да, вот, собственно, я хотел задать вопрос на лекции. В чем, собственно, разница между коммутаторностью и по сути, очень похоже.
Да, но проблема в том, что в произвольной пленочке, которые в технологии происходит, никак нельзя разрешить особенности. А вот представьте, например, самое простое. Стол, да, равномерный. Это один конус. Если то это цикл, то есть цель, которая пройдет в этой точке. Как мы называем? Не как близко, а как конус на сторону.
Особенность многообразия.
Да. Вот. Сторон, ладно, можно взять и заполнить.
Как-то заладить.
Но факт в том, что если вы берете цифр 2, 3 как не является никакого.
Получится подвальный баланс.
Нет, просто цифр 2 не не является позицией, примерно здесь можно что-то придумать, какую-то процедуру разъяснить, органической точкой, как он нравится.
Да, я увидел.
Да.
No, this course yeah, I think that this course will do no, it's one course. Maybe he will get something in spring, but yeah. No, he teaches seminar in MSU. I think that it's like seminars with standard course of topology, so it's like for professional topology. Yeah, not only topology, just in
Let's continue. But I hope that on this part it will not only me who will speak. Okay. So I would like to start with one problem, which is actually, it shouldn't be a problem, it should be an easy thing, but I have experience for three times I asked this for students here, and the count is two against one. Two times it caused great progress, but once not. So I hope today we will quickly go through this, but still. Okay. Let us consider the differential of a function. just the easiest thing which we can consider. The matter is that it is a well-defined linear, as I have written, it is a well-defined linear function on vector space. F at each point is a well-defined connector. This is a invariant formulation. A non-invariant formulation is that, okay, if we consider what is df non-invariantly in coordinates, of course it is just the sign like that, where of course we have this summation over I, and it is a well-defined functional vector. So if we have some vector ci, then of course we can pair it off, and we obtain this is a well-defined value which is independent on the coordinate system. Well, my question is about the second differential. If we consider the second differential, not in the sense of d times d, of course this is 0. It is not d of d, it is just, we can consider the, here we have n numbers which are partial derivatives. Here we have n squared numbers which are second partial derivatives. The question is whether we can organize it into a well-defined quadratic function or bilinear function of two vectors. This is the same, of course. So whether, of course, this is by no means a two-form anyway, since it is not skew-symmetric but it is symmetric. So this expression is of course symmetric, but the question is whether it is well defined.
You mean with respect to coordinate transforms?
Okay. Here we have invariant description and coordinate description. Here I write down only coordinate description, and the question is, these are equivalent questions, whether there exists an invariant description. And the equivalent formulation is whether this coordinate description is independent of the coordinate system. So these are two equivalent questions. If it is invariant with respect to coordinate system, then of course we will found an invariant definition, and vice versa. Okay. That's a question which I said.
It will be invariant if first derivative is 0.
Yes, and if not?
No, I think we need something like matrix. No.
Why? Just this expression.
No, it would like.
Well, direct coordinate transform would hardly turn with the first.
Okay, so I suggest that somebody do this. Just this is an easy thing, but I prefer not to have problems further with this. I want that we are sure that we understand this. Good something just. Okay.
I should speak in English, right?
I think yes.
I will try. Well, we can consider Taylor series for the function f in coordinates. It will be 0 plus this. And plus second term, maybe with 1 half.
XI
Ой,
is the denominator.
yes. And plus something which is less. Well, if we now apply coordinate transform, it will be something like this. It will be by. We can also write Taylor series for coordinate transform. It will be at first term linear, and maybe there were higher terms in the, well, some linear function of new coordinates. Let us name new coordinates new. So we will have some linear of new plus quadratic.
Do you mean again XI? Or XI?
Right,
Yeah,
right.
here. Is it
Yes.
XI or XI? Okay.
It's, ну, это не сильно важно, просто обозначение. So now we put this expression here, and we get that if this term is 0, then we have linear to quadratic term. We have to look only on linear terms here. So this will be invariant if we do linear transformation. But if this term is not 0, the quadratic terms from here will destroy invariance of the whole thing. Because they will appear here. Is it enough explanation?
Well, more or less, yes.
Well, it could be written explicitly with
It could be.
coordinate transforms, obviously.
Well,
It could be written explicitly with coordinate transforms.
yeah, sure. Well, thank you, but maybe still we write it explicitly. Maybe it will be useful.
Can do.
Can you do? Sorry.
So, if I may. First, let's consider the first differential. Alright. Assume we have x prime, or maybe, alright, it's y. This here, y is another set of coordinates. So we could do this way. Something like this is. So the differential by any of the new coordinates can be expressed as a linear function of the differential of all coordinates. Here, summation is implied in the repeated index. As an aside, repeated indices are in Greek letters, non-repeated are in Latin letters. Now, assume we do the same with second differential. So,
Well,
this is simply a repeated application of this construction, but for two different indices. Alright. So let's see. Is it seen there on the camera? Is what part of the board?
I don't know.
Can someone check it?
Не очень. I think you can go here. Just.
So, and now when we apply these differential operators to this construction, we need by Leibniz rule to apply it to each of these in turn. The summand this differential operator falls on this construction. We get this is what we would like to have. The other part, of course, is where this differential operator acts on this construction, which is might have non-zero derivative. And then we have let's just keep that term at this.
Well, stop. Let's discuss this term.
It should be actually
What is this, and does this expression has any sense?
it should be done another way because
What is a partial derivative? A partial derivative is a derivative when all other coordinates, all other variables, it doesn't mean whether they are coordinates, all other variables stay constant. Yes? Look, this one,
actually
this derivative is taken when all other x's stay constant. This derivative is taken when all other y's stay constant. How to join them together?
actually should have done easier. I shouldn't have transformed that entire construction, which is I should have simply applied this to this,
What?
as in this is a transformation of this operator.
Yes.
Should have simply applied this.
Yeah. So what is the problem? Once more, what is the problem? Why this thing is not well defined? The matter is that for
different coordinate system.
well, they're different. But what's the real problem? When you deal with usual partial derivatives, then they commute. This is one of the first properties in mathematical calculus development. If you take if you have function of two variables, then of course you have this.
That assumes a single system. Perhaps.
Yes, but these two derivatives do not commute. If you first take derivative by yi with constant otherwise, and then take derivative by x lambda with constant other x's, or in
other order, the result will be completely different. So hence it is better not to write it in this way.
So it means that the Lie bracket of vector fields is
Yeah, the Lie bracket of this vector fields is not zero. The Lie bracket, this is the same to say. The Lie bracket of vector fields corresponding to coordinate system, we have coordinate vector fields. Their Lie bracket to each other are zero. But if you consider vector fields for one coordinate system and for another, there will no reason why it is zero. Well,
That way is better.
well, why? No, I think it's too easy. No? Well. It's one minute. Yes. This is just
No.
okay.
That is, we apply this operator to here,
Yes.
but this to that. Since these are just
Yes,
two
yes,
different
yes.
expressions for the same differential operator,
Yes.
this works.
So
So we
Actually-
have this additional summand which
okay. Yeah.
breaks what we wanted to have.
Thank
Unless, of course, we have zero in whichever.
Yeah, that's exactly what we need. So if we had only this expression, then this is usual law for transformation of bilinear function when we change coordinates. But we have this additional, and if this is non-zero, then it is not well defined. Well,
It's literally the same.
yes, that's literally the same, but maybe sometimes it is convenient to have this formula. Yeah, of course, both explanations are good. What will be important for us here? First of all, important to know that it is not so good, and we cannot use second differential as an invariant object in arbitrary situations. This is just to avoid some mistakes. But the second, and this will be important in the second part of the course, when we consider Morse functions, it is very important that the second differential is well-defined. It has this independent of coordinates in those points where the first derivative is zero. Well, okay, just we have discussed it, and let's keep it in mind for the future. Well, second thing which I would like to discuss is, okay, maybe it's very easy, but just let's speak about it just several things. Some things should be said. Okay, if we have a usual circle, what can we say about its Durham cohomology? Very easy question.
It is real numbers in each complement. One dimensional.
Yes, first of all, a zero-dimensional cohomology, of course, is R for any connected manifold. This is obvious. The matter is that the first-dimensional cohomology are just zero forms, that is, functions, which are with df equals to 0, so locally constant functions. On a connected manifold, it's just constants. So zero-dimensional cohomology is constants, and this is for any connected manifold. And what we for circle we have that this is R, and what is the generator?
It is
Yes, it's just
d phi, where phi is not a k-form, but phi is a polar coordinate. Okay, what is important here is, though it has been noted by d phi, it is not an exact form. The matter is that phi is not a well-defined function. Phi is a multivalued function, and actually, exact forms are exactly differentials of multivalued functions. The matter is that locally they are, closed forms are always differentials of multivalued functions. Locally they are exact, but globally not. Okay, and why it is exactly R? Why of course, how to obtain this?
From integration.
Yeah, it's just integration by S1. So any form, I would like to use another letter, not phi. Any one form goes to the integral over S1. And of course, we have a homomorphism, and of course it's surjective since d phi goes well to 2 pi. Yes. Why it is an isomorphism?
No, we can deduce it from Meyer-Vittorius. We can take to cover of circle and see it.
Yeah, there are two possibilities. First, we can deduce it from Meyer-Vittorius by taking such cover, but 2 half circles, but we should take some greater than 2 half circles. Yes. So something which is slightly greater than half of a circle. And but this is in this particular case, of course, it is easier to do it directly. How to do it directly? The matter is that if you have got an arbitrary exact form. Oh, sorry. Just an arbitrary one form. Sorry, my English is so that I always miss. Все время путаю слова exactly closed. I'm sorry. This is just English. If we take any one form on a circle, any one form is of course closed. The matter is we do not have 2 forms at all. So any one form is closed. So we just need to take the quotient of all forms by exact ones. Well, but for any one form, what can we do? We can do that. And this is a one form, a new one form, which has 0 integral. If it is theta prime, then the integral of theta prime is 0.
Hence it is.
And hence, when we consider multivalued function with this differential, when we start integrating, then after this pass, or after this loop, we arrive to the same value. And hence, theta prime is the differential of some function. And so what we see that any theta is homologous to a multiple d phi. So we see that it is an isomorphism directly. For of course with circle it is rather easy, but still it is okay. And if we proceed further, then of course in a similar way we can consider all spheres. Let us use the first strategy with Meyer-Vittorius. Yes.
Yeah.
If it is not S1 but Sn, then we can decompose n-dimensional sphere with 2 parts, each of which is slightly greater than half of the sphere. And well, one of them is U, the
second is V. What do we know? We know
where
that
intersection it is no gamorphic equivalent to
yeah.
smaller dimension, low dimension.
First of all, U is just diffeomorphic to Rn, and V is diffeomorphic to Rn. Hence, we know very well they are cohomology groups, and they are just trivial. Yes, except for dimension 0. Yes.
No, yeah. Hence, we need to look only at the connection.
Yeah. Hence, connection homomorphism is, let us write it. Yes, connection homomorphism says that says that HK of the intersection, yes, is isomorphic to HK plus 1 of Sn. Well, except for dimension 0 and for positive. Okay.
Yeah. And then we use
and-
induction using
yes.
the fact that intersection is.
We use induction, but we need one important fact. We need homotopy invariance of the rank homology.
Yeah.
And this is what I suggest we discuss now.
No, it follows from Poincare limb because intersection will look like sphere times.
Poincare lemma relies on the fact that
Yes, but
forms can be transported by.
actually, in this particular case, in this particular case, we have not only homotopy equivalent, but we have just that it is diffeomorphic. It is even more. It is diffeomorphic to this one.
And hence we can
And
use-
hence it follows exactly from the exercise which I considered, which I suggested you do. But I suggest that you do that exercise. If you don't know it exactly, it is a useful one. Actually, it is true that the rank homology are homotopy invariant. Maybe I will leave it to the second lecture. In the beginning, I will briefly recall how to prove this accurately.
No, because in general case, by similar reasons, like in Poincare lemma, we
Yeah.
need to construct chain gamotopy by integrating from U dt, like this.
Yeah. All these results are of the same nature. But actually, from Poincare lemma, we just can deduce from it. Not at the same spirit, but just from it. We can deduce that how much they vary. Okay, but at least here we understand well that it is. Okay. Well, and one more thing. Which is important is that also this thing is also rather easy, but again let us mention it. Assume that we have that our manifold is closed in the sense that compact without boundary. Connected and oriented. And then what can we say about the top homology, the homology of this M?
No, it is always generated by orientation form, volume form.
What definition of oriented do you use?
Because of oriented. Okay. Yeah.
Because yes, there is a way to define orientation by having a non-vanishing form of the dimension.
Yes, but actually I would prefer a more. Okay, we just can we have an atlas of charts so that translation functions preserve orientations. Yes, so we have orientation on each chart which just lives in Rn, and they have orientation that agree each other. Okay, how to actually, I think at the moment we do not have enough tools to understand that this is exactly R. We can understand that it is at least R. And how to do this?
Maybe using my victorious also. No, but for bigger coverings.
Okay, if we use Maya-Vitores, then at this point we can decompose it, but it is arbitrary manifold that we have not very easy intersections and so on.
We can use the end forms spent by.
Yeah, first of all, let us just write down a generator. First of all, this S for the circle, what do we have? We have a homework here. If it is oriented, then we can integrate N form. N form is always closed, and we can integrate it over N. Yes? And and this is epimorphic. Why? Just because you may easily find out. There are two ways. First, you can just consider a form which is not zero, only in some neighborhood. You can easily write down explicit form in Rn, which is concentrated around the origin and which integrates, say, by 1. Yes? But then another way is that it is useful that once we introduce a metric, we can very nice volume form. Just as I just mentioned it, that if you have introduced a metric, remaining metric on M, remaining metric on M, then you just have a volume form which is characterized by the fact that its value on n vectors is just the oriented oriented volume of the parallelepiped spanned by this length vector. Yes, once we have Riemannian metric, and orientation, we can speak about this. And also, it is an important thing that we can write down it explicitly. Where G is the determinant of it is a good well, okay, just because this volume form is because this volume is just the square of the ground matrix, and this is this gives the sign of orientation. So just it is useful that we always can write it down explicitly. Why the question of why this is exactly R, it is slightly more difficult, and we will discuss it after we speak about the Debye duality. Okay, and now these were all easy. examples. And in fact, the first example, which is not as easy, starts what is the most important manifold after Rn and the sphere?
Maybe projective.
Yes, but CPN, not RPN. RPN is not so interesting. And
Not so interesting.
RPN, of course, is not so interesting as CPN. RPN is something which is okay. It is just the quotient of a sphere. But the most important manifold is CPN. I recall that, okay, it is just the set of, it has homogeneous coordinates. So we consider all non-zero vectors in Cn+1 and take the quotient of the action of algebraic force. So we have these homogeneous coordinates, but we can easily, we have n charts, yes, in a standard way. The first of them is non-homogeneous coordinates are such quotients, and they are defined whenever the zero is non-zero, whenever this denominator is non-zero, and at every point at least one coordinate is non-zero, and so we can, the union of these charts is the whole CPN. Well, and those of you who deal with at least some cohomology theory, doesn't matter whether you consider singular cohomology or something like that. An important claim about CPN is that it has, if say you consider usual singular homology with coefficients in Z, then you have such answer. The answer is reduced polynomial ring. You take polynomial ring and you take the quotient by such ideal where the degree of U is 2. And of course, for de Rham cohomology, actually in several lectures we will prove de Rham theory that de Rham cohomology are isomorphic to usual singular cohomology with R coefficients. So of course we should have the same answer, and so now I would like to use de Rham cohomology. I will not speak about, and so about singular cohomology. So now this means de Rham cohomology, and of course we should have this answer. This is the quotient. Yeah, one important thing, of course, de Rham cohomology is always a ring, because we have multiplication of forms, yes, and it induces multiplication of cohomology classes. But this is the answer, and to understand this answer, it is important. It is well. What do we need to understand this answer? We would like to have the generator. So the question, the problem is how to construct the generator. That is, we would like to have to form
phi in CPN, which is closed and which has non-trivial homology class. Well, what is the usual approach to such problems?
I think we can, by induction, find such form for the case n equal 1, and then take pullbacks for larger n.
No, you can't take pullback. The matter is that the matter is
sorry,
in the opposite direction. If you have this form for CPN, of course you can restrict it to CPN minus 1, but not
Maybe
vice versa.
maybe solve differential equations.
There are two. Okay, there are plenty of them. Look, of course, this solution is not unique. Of course, this solution is up to an exact form. There are plenty of exact forms. I just write down an arbitrary one form, and I can add its differential. So if we just write down these differential equations, first of all, they are complicated. Second, we a priori know that they have plenty of solutions. So it is rather hard to expect that we can guess a solution.
Maybe we can take generator of homology class and
Yes, for those who, if we know usual homology theory, assume that we know it, then we know that the generator of second homology is just CP2. Yes? It's the class of CP2 inside, CP1. CP1 inside CPN. CP1 is two-dimensional, which is just S2, yes? CP1 is just two-dimensional sphere. And so this is just a generator. So of course we understand what do we want about this phi. We want that, we want this, and also we would like that integral of this phi over CP2 is non-zero. So this helps us to understand what do we want, but it doesn't help us to find this phi.
As I
nice
remember,
symplectic form.
yeah.
We can get it from quotient by
Yes.
symplectic reduction.
No, but by definition, it is the same task to find
Yes,
some.
if you know symplectic
Close
reduction,
close.
then you can obtain it from there. That's good. Actually,
As an aside, could we use the short exact sequence from this sphere?
using yes, actually it is also possible, but in fact we can consider what we can consider. We can try to proceed by induction. We can consider Cp n minus 1 inside Cpn. For instance, how? Particular Cpn minus 1, just where Zn is 0. Yes? Then we have decomposition of Cpn into two open subsets. First subset will be a small neighborhood of Cpn minus 1. Yes? What is a small? Okay, small neighborhood. For instance, for instance, we can write it down explicitly. One of such small neighborhoods. Say that n is less than all other coordinates.
This is a good. Okay. In fact, we don't need to write it down specifically. We just small neighborhood which we using homotopy invariance. We know that it is homotopy invariant to CPN. If we need, we can write it down explicitly. And the second set is just CPN without CPN minus 1. Yes? Which is just, if I wanted to see it, since this is just a chart. So, we know the ramp homology here, we know the ramp homology there, and we can easily write down Meyer-Witter's sequence. I suggest you do it, and when you do it, you easily see that at least additively you can get this result easily, that you have R in all even dimensions. It is not so hard, but actually on this way, it is not so easy to find out an explicit generator. Well,
we understand we need to find some partition of this.
yeah, to find an explicit generator, you need to do it all these things explicitly. You need to write down U explicitly and so on. It's not so easy. And first you need to guess first how it does look and to proceed by induction. And actually, symplectic reduction is also a good idea, but for those who know about it. So I did not think that you suggest this. Actually, there is another possibility to approach this result. But okay, I think that we will discuss symplectic reduction too, but maybe later. Another possibility is as follows. Look, what is nice about this manifold CPN? Well,
It's complex manifold.
it's complex manifold, it's also nice, but a nice thing about it is that it has plenty of symmetries. It has great, just very large group of symmetries. What is the group of its symmetries? Of course, we have all its diffeomorphisms, which is group with which it is very hard to work with all diffeomorphisms of a manifold. So it is not a good group. But a good group is, of course, we can say we can consider such group. We can consider general linear group over C, and just we should take parameterization. The parameterization is just the quotient by scalar matrices. Of course, scalar matrices produce trivial automorphism of CPN. And this group acts naturally on CPN. It acts by diffeomorphism. A natural idea is the following. Suppose that our problem has some symmetries. Maybe it is natural to expect that the answer will also have such symmetries. Maybe a good idea is to try to look for invariant form, for the form which is invariant with respect to all these symmetries. And then
it may turn out that there are not so many equations, and the equations are not so hard, not so complicated. So if we have plenty of symmetries, then maybe when we restrict to invariant objects, the equations become not so hard. And it is, but this is a good idea, a bad idea. A good idea, but bad realization. Actually, if we try to do this, we obtain that there are no such forms. Why? The matter, well, it is just very nature that we can't. It is too much. We want to have too much. Look, even if you consider a circle, then you cannot. We cannot hold that there is a form which is invariant with respect to all the finite transformations. Yes? Because
They are not preserving volume.
they are preserving volume. It is, we do not know why volume is important here, but what is important, and important is compactness. A good idea is to take a compact group here. Which compact group is here?
S and then no, P is.
Not S, but just projective unitary group. Okay? Why this is good? The matter, okay, this problem, we know that this problem has a solution. Yes? We know that, at least we hope that it has a solution. There is such a form that satisfies these properties. Okay? If we have a compact group of symmetries, then this is a general idea. We can always average this form with respect to the symmetries. Yes? So if you have, in general, if you have a compact group that acts on a manifold, and you have a form here, then you can take integral over this group by such forms. Well, and if we had a solution, we will obtain an invariant solution. So we a priori know that for a compact group, there must be an invariant solution. Well, for non-compact group, we have no way to average it. We cannot hope that we have an invariant solution, and in fact, for a non-compact group, we do not have an invariant solution. But for a compact group, we a priori know that since solution exists, there must exist an invariant solution. So the next step is to find.
Sorry, what do you mean by this integral?
The group is a compact Lie group, and then
Yes, that's a Lie group, so this is integral over the group.
Why doesn't it work if you take the average for discrete?
Yeah. This is an integral, not all. This is well.
a Lie group is a manifold.
Yeah.
You can
We need to distinguish between integrals of the first and the second order. This is not an integral of a form. This is an integral of this form. This for each g. If phi is a closed form, then for each g, this guy is a closed form as well. We just apply symmetry, apply some diffeomorphism. So this one is a closed form, and a closed form is just an element of some vector space of closed forms. And now we consider this not as a form, but as an element of vector space dependent on an element of a group G. Dependent continuous. And this is just a vector valued continuous function.
And we take integral with respect to some metric of this group, invariant metric of this group, we will take such integral. And what we get? We get again a closed form. Since we just can take the order of differential, just we differentiate each form separately. And so it is closed, and the integral will be the same, just we take the, it is better to take the average, so to divide by the volume of this component. So we may achieve that we again have obtained a form with the same properties. So this is some trick, but it is very often trick in the problem that if our problem has some compact group of symmetries, then we can expect that if the problem has a solution, then it has an invariant solution. Because if we have any solution, we can average it over the group of symmetries. So we can look for an invariant solution. And now the problem becomes much easier. And that is what I suggest that you try to do. You just try to write first an invariance condition. So how many, let us forget about this condition and that condition for a moment. Let us just ask yourself, how do invariant two forms on CPN look like? So can you write down an arbitrary invariant two form? And after you do this, you just substitute this arbitrary two form here and here. And it turns out that you immediately get a solution. So I suggest that you try to realize this approach. But it's important that we take only this compact group.
Is projective unitary group the same as unitary group?
No.
No, it's quotient by bias one.
Yeah.
By scalar matrices. Of course, scalar matrix is unitary only if the eigenvalue is this diagonal entry is on the unit circle. But well, how to think about this? Well, actually, we have CPN.
Actually, what is PSL?
Well,
What is PSL?
uh,
It's hard to imagine.
well, what is this? This is just the quotient group of unitary group by. Yes, it usually you don't need to write down C here, unitary, so this is for C. The quotient group by diagonal, some group which is U1, which is embedded here is diagonal. But actually, well, what do we need? We need that, look, to apply, what is it to form? To form is just a function if we take a point here and two tangent vectors, C and theta, then to form has a value, it may take the value at point P on these two vectors. Well, to form is a bilinear form on tangent vector space. So the answer should be invariant if you apply to this triple P, C, and theta a unitary transform, the answer should be the same. So the question is just to find all bilinear forms of two vectors which are invariant under all unitary transforms.
No, I think just intuition. We know that U it is a group that remains some how it is named? It is bilinear form on complex space.
Yeah.
The most obvious example it is, but it's not bilinear. It is Hermitian product. So if our two form would look like some this fixed form, maybe this group automatically will remain this form. For example, if you take Hermitian form like sum of ZE times ZE conjugated, and then take some two form analog, for example, like DZE conjugated and take sum over all indexes, maybe it would be invariant.
Maybe it is very close to what should be done. We should be more delicate here. We want not Hermitian form. This phi should be not Hermitian, but a real bilinear form. So we could slightly and also there is we could take care about this p.
Maybe it's sufficient to pick to form in tangent space in one point, and the only условие is that it's invariant.
The first, indeed, the first step is as follows. Of course, by unitary transform, we can take any point of CPN to any other point of CPN. So, of course, it is enough to write down this. Let's consider the simplest point of CPN, say this one. Yes? And let us consider the find a two form at this particular point. So just this is a question of linear algebra. A bilinear form on one particular vector space, which is invariant not over all unitary group, but over all unitary transformations that preserve this point. Yes? And when we find all such forms, we just extend it to the whole CPN by the action of the whole unitary group. Yes, so the question is just about a form in the tangent.
Actually, can the form itself be extended by action of a group or the CPN? Or only the averaged form can be extended?
Only which?
Let me explain. We take a form order point. We take two different elements of a group.
Yeah.
Which
Look, good question. If we have this point A0 and you have another point P, yes? And assume that we have already understand how our form looks at P0. So we can consider the two different elements which take P0 to P, yes? And we can extend the form here using G1 or using G2. The question is whether the results coincide, yes?
Yes.
But
We can understand what the averaged resultant will be the same.
The matter is that if we go along G1 and then return along G2, then this is an element which preserves P0. Yes?
Mm.
Oh, of course, since both. So if our form in P0 is chosen so that it is invariant with respect to the stabilizer of P0, then the result of an extension is independent.
Then can we take an arbitrary form and average it over the
Yeah.
stabilizer?
Yes, this is exactly what I suggested. Just to take an arbitrary form of this vector space and average it with respect to. Actually, a good use is that if you do it, if you do this, yes, actually you find out that the form is unique up to multiplication. An invariant form is unique up to a multiple. And it will automatically be closed. And if a multiple is not zero, then you need not. In fact, we will need. We do not need to solve this equation. It will be trivial. When you find this invariant form, it turns out that in this particular case, when we decided to find an invariant solution, just there is one invariant form at all. Yeah, up to multiplication by a non-zero real number. And if you find this form, then you automatically obtain that it is closed, and hence generates the second homology. But we need to find.
Sorry, if I understand, we first need to find the stabilizer of this equation.
Yes. We need to find a stabilizer. We need to find a tangent space explicitly. The matter is that okay, we need to work with it, so we need to identify it in some way. We need to just to solve a problem of linear algebra.
Shouldn't it be just like Hermitian product?
Hermitian product is
It's not
Hermitian.
anti-symmetric.
We would like to have skew-symmetric real linear form. So it is closed, but it is not completed.
No, it's clear that stabilizer is unitary on one and less.
Yes.
And no,
Yeah, the stabilizer is unitary group of dimension n. Or not of dimension, UN.
Why it is clear?
Well,
Why it is clear that stabilizer is stabil?
oh,
Stabilizer.
well, you would like to have. Let us for a moment forget about projection. For a projective group, if you just start thinking about unitary group un plus 1 x in Cn plus 1. Yes? And we are interested in the stabilizer of the vector. Well, how does the stabilizer look like? It must have first column of zeros. Yes? Because this is just the image of the first of that vector. Yes?
Well, not necessarily one, but after projectivization.
Yeah, I say first without projectivization, and we need to have zeros here because columns must be pairwise orthogonal. So, and of course we have unitary matrix here. So we see that this in UN. Oh, what now about projectivization? If we take a projective group, yes, then we need to stabilize not this vector but this point on CPN. So we may have here not one but some element u, some complex number with unit norm. Yes? We still have so this stabilizers a point on CPN. Yes? But still here we must have zeros. Yes? And here we have some matrix. But look, all this is a unitary matrix. But our matrix is our element of projective unitary group is not a matrix, but it is a matrix up to multiplication by a diagonal matrix. So we always can choose this diagonal matrix so as to obtain here true unit. Yes? And then we have no more freedom in choosing this matrix. Once we choose this normalization so that we have unit here, we have no more freedom. So the stabilizer is exactly not PUN, but exactly UN. The stabilizer of a point. So stabilizer in PU and plus 1 of a point is just UN, not PUN. And this is the explanation why. And we have, indeed, we have standard action of this UN on a tangent space, which is a dimensional complex. So this is just the question of you have usual n-dimensional complex vector space with non-degenerate Hermitian positive definite form. So just very standard situation. And we are interested in R-linear skew-symmetric forms which are invariant with respect to the unitary group. So this is just a reformulation. Well,
I think I can try to.
So this is just linear algebraic reformulation. You do not need to think about some differential geometry anymore. Just you have this situation, Cn with standard Hermitian forms, Hermitian. And what we are interested in, we are interested. Okay, I prefer not Cn, but let us think invariantly. So, n-dimensional complex vector space, yes, with positive definite. And we are interested in bilinear forms, R bilinear forms, which is R bilinear and skew-symmetric and invariant.
That means that we can diagonalize it in an orthogonal way.
Yes. So
And by this you have that it should be a standard form in some orthogonal basis.
yes, but what is this standard form?
dx1, dx2 plus dx2, dx.
Well, this is in coordinates. Yes. Actually, it is.
How do we write
First good question is that this one is unique multiplication by number. This is what should be proved. And then, of course, if you write it in coordinates, you get like you say, and then you need to return here and get this representative. But now we are out of time, so I suggest you try to do it till. Yes.
yes.
Now we finish our time. So I suggest you try to do it till the next lecture, and we discuss it. Okay.
А почему это действие n будет стандартным?
Почему оно будет стандартным? Надо просто написать, проверить. Оно будет стандартным.
Я размерности вариант.
So, that's all for today.
Окей, я все сначала запрашивал. А вот зачем мне нужно было?
Я
фиксировать точку.
Фиксировать точку? Нет, просто как сказать, вариант формула, какой вариант формулы, она должна быть в каждой точке. Ну и она имеет. Задачу достаточно, не то, что
Просто хотел спросить, может, мы можем добавить
именно в этом смысле. Но искать важно что? Сначала найдем точки. Нет, так просто действует. Сразу. Сейчас,
Я на четвертый.
Because it's a large group. No, complex numbers is connected. When we replace it with
сейчас найдем
but it is not complex. Because it is, it is too large group
Если некоторые
to form the with respect to this. No, we have a lot of functions. No, G then is
Ага, а там.
ну, calls
Да, по курсу лекции две главные книжки такие.
ну, это
Во-первых, положение называется дифференциальной формой по
because it is no, just usually is the opposite subset of the space. No, in the space of the nodes. So it is open in some non-complex. That's why it is looks like this equation that something is not. That's why it is not open. If it is open, it looks like zero of some equation. Then it is non-correct.
Примерно.
Где написано про теорию Черновееля?
Теория Черновееля. Ну, Про него где-то так не написано, а я хотел нашать. Мне больше всего нравится написано
В то же самое время.
там очень кратко, но очень правильно.
Типа,
Милого старшего там приложение.
я хотел начать приложение, которое
Класс, милого старшего, да, с другой стороны. Класс совершенно. У них есть такое приложение C, опять где очень кратко. Там вообще приложение милого старшего такое золотое приложение просто это не знаю, страничек на 10, все, что нужно по секунду. Ну, кроме спектральной последовательности. Все, что до этого, все это написано. Но сейчас есть какие-то более такие варианты. Чуть говоря, у меня вот это
Потому что такое второй дифференциал. Ну, первый дифференциал можно найти в выражении STM в R, второй это STM в R.
Нет, это есть, я не знаю. Типа даже базовые теории.
Yeah, I was.
Нет, что люди рассматривают. Я сказал, что это больше больше анализа, чем никто не приходил. Причем есть проблема.
Про теорему Фрейда слишком не будет.
Не, ну этого есть, это дальше это можно проговаривать такие частично, это по-другому, такие как геометрия. Я это когда мы от функции оставляем
А может быть трансляцию остановить?